So, how do you even begin to measure a universe? A universe that has things as ancient as a galaxy, and at the same time something as unbelievably fast as the vibration of a single atom. Okay, let's dive right into this, because if we're gonna understand reality, we first need a ruler that's big enough and small enough to measure all of it.
Just look at this for a second. On one side, you've got the Andromeda Galaxy. It's been around for 10 billion years. And on the other, the vibration of a cesium atom, an event that happens over 9 billion times every single second. So how in the world does science create a system that can meaningfully describe both of these things? That's the huge challenge we're going to unpack.
All right, so to get a handle on this incredible range, scientists started by, well, classifying the extremes. They basically drew a line in the sand, separating the entire universe into two totally different realms, the world we can see and the one we can't. And that line separates two really fundamental ideas. First, you've got the macro world. That's everything on a large scale, the reality we see and interact with every day. But then you've got the micro world, this invisible subatomic realm that, and this is the crazy part, is the foundation for everything in the macro world. And to make it super clear, the macro world is home to things like stars, cats, and trees. Pretty straightforward. The micro world, on the other hand, is the world of atoms, molecules, and ions. So the big question remains, how do you possibly measure two completely different worlds with the same ruler? So now we've got these two worlds, the visible and the invisible. How do we study them together? Well, we had to develop a common language, a universal system of measurement that could describe all of reality, from the biggest galaxy all the way down to the tiniest particle. Which really brings us to the core of the problem, right? How can we possibly describe a galaxy and an atom using the exact same set of rules? I mean, what would those rules even look like? The answer, it turns out, starts with a concept called the fundamental quantity. The best way to think about these is like they're the absolute, can't be broken down any further building blocks of measurement. They're kind of like the primary colors of physics. You can't create them by mixing anything else together. They just are.
And here it is. This is the brilliantly simple solution. The entire international scientific community agreed on just 7 of these fundamental quantities. This is what we call the International System of Units, or SI for short. With just these 7 building blocks, length, mass, time, you see them here, we suddenly had a toolkit to measure the entire known universe. So now that we have this powerful new language, let's put it to the test. We're going to take a quick journey through all the scales, zooming in from the cosmic, way out there, all the way down to the subatomic. We'll start out at the truly gigantic, the cosmic scale of galaxies, measured in billions of years. Then let's zoom right into our familiar macro world, the scale of a cat's life, something we can all easily wrap our heads around. Now we're pushing way past what our eyes can see, entering the microscopic world of a single red blood cell. Until finally, we land on the fundamental building block of matter itself, the atom. In just a few moments, we've traveled across dozens and dozens of orders of magnitude, and all of it is describable with the same basic language. Okay, and this brings us to a really important point. The language of meters and seconds might be universal, but the tools we use to measure are incredibly specialized. You can't measure a galaxy with the same gadget you use to look at an atom. For the macro world, we need giants like the James Webb Space Telescope. For the micro world, we need instruments with unbelievable precision, like atomic clocks. But this is where the system gets really, really powerful. You see, these 7 fundamental units aren't just for measuring 7 things. They are literally building blocks. By combining them, we can create entirely new ways of seeing and understanding the universe. We do this by creating what are called derived quantities. And really, it's just what happens when you combine the fundamental units. You multiply them, you divide them, and by doing that, you build brand new concepts, new lenses to see the world through. Let's just take a super simple example. You start with one fundamental quantity, length, measured in meters. You grab another one, time, measured in seconds. You just divide length by time and boom, you've created an entirely new derived quantity, speed, measured in meters per second. And this idea, this principle, it works for everything. Mass divided by volume gives you density. Speed divided by time gives you acceleration. All of these complex, powerful ideas are all built from those same 7 simple blocks.
It's incredible. So, what's the big takeaway here? What does all this mean? Well, it means that creating a universal system of measurement does something way more profound than just sticking numbers on things. And this right here is the core idea. By developing this new technology and a consistent language to understand it, we have literally expanded the universe that we are capable of experiencing. We can now see the vibration of an atom and the birth of a galaxy, all because we figured out a consistent way to measure them.
And in the end, it all comes back to this one number: 7. Just 7 fundamental units that give us the key to understanding everything, from the tiniest flicker of an atom to the mind-boggling age of a galaxy. Which, of course, leaves us with one last, really exciting question. We've learned how to measure the incredibly small and the incomprehensibly large. So, with this amazing language of science we've built, what invisible worlds will we learn to measure next?